Building on conditional probability, we can now move on to probably one of the most important rules in probability, the almighty Bayes rule. But before we move on to the Bayes rule, I would like to introduce the concept with a use case. Let's think about the use case of pregnancy, and we are measuring one biomarker that we obtain through plasma, and we can build the statistics of this biomarker for using all the data that we acquire all around the world, right? So we can talk about a probability distribution of one thing, probability of A, and let this A be the biomarker. And of course we can build the distribution of this A. Let me not close the parentheses yet. Let me go ahead and draw the probability distribution here. Let's assume, for the sake of simplicity, this is, let me take my green. This looks like Gauss, just like everything else. And I intentionally did not close the parentheses here. We can of course condition this probability distribution on something, right? So we can calculate the probability distribution of women whose pregnancy end up with a miscarriage, unfortunately. We can condition this on B, and we can call this miscarriage, and we can have a probability distribution of probability of A given B. Similarly, we can have another probability distribution that's going to give us the probability of A given not B, healthy birth, and that's the one that we encounter even more. So for any part in this measurement, we can now calculate what's going on, what's the probability of this biomarker for different conditions of the pregnancy, either miscarriage or healthy birth. But the more interesting question, or the probability that the couples want from the doctor, is not the probability of biomarker given miscarriage. So they go to doctor every now and then, and they want to have a probability, 1 in 10,000, 1 in 1,000. Sometimes the doctors are supposed to give the probability that's given their measurement of the biomarker for the couple, for the woman. They want to learn about the probability of miscarriage, right? So the interesting question is not the one that we can model, that's easy to model. The interesting question is the one that we cannot directly model for everybody. So the interesting question is the probability of B given A. So that's what we want to answer. But obviously, giving a probability for any kind of for any value of the biomarker that we measure, at least building it using the frequentist approach, is not possible. So we cannot possibly measure or collect the data sets for any kind of any number of biomarker levels, and we cannot wait until many miscarriages happen, right, for certain values. So we need to do we need to act in a smarter way, and we need to do something extra. For this, what we do is we use the conditional probability rule, and which is going to evolve it into the base rule. So we would like to give a probability of miscarriage for the measurement that for this specific person, and this can be obtained from probability of, we know from the rule of conditional probability, this can be obtained from probability of AB divided by probability of A. And again, as we are moving with math, it's always useful to pause and ponder what each and every one of them mean in application, and is it easy for me to model or get this number. So first one, we have an understanding. So this is relatively easy. We can think about a data set in which on the one hand side the measurements of the biomarker for healthy patients, healthy pregnancies, and biomarkers, the list of numbers for unhealthy or miscarriage, the pregnancies that end with miscarriage, and we can easily draw these histograms, right? And but they are not easy, they are not directly applicable to our use case. On the other hand, the joint probability of the miscarriage and the biomarker, so that's not easy to directly model. And also the denominator of this equation, which is the probability of the biomarker that we observe. How rare is this number? Say 3.7. How rare of 3.7 milliliters per centimeter square? How rare is this? This is also difficult, but we will move on. We know that the joint probability, so this probability of AB can also be obtained from the thing that we can observe. We can actually measure, right? So we said we can actually model probability of A given B, and which is also probability of AB divided by probability of B. Again, during this derivation, I'm writing pure math, but I want to keep describing what it means in our use case, and you can take it to all of the use cases. Again, the probability of A given B, probability of observing this biomarker for healthy or non-healthy pregnancies. Again, the difficult thing, and this is relatively easy, right? So from our distribution or data set, imagine it's Excel sheet. On the one column I have a list of pregnancies that end with healthy birth and that end with miscarriage. You can calculate the prevalence of miscarriage, but using this I can actually, so I have two easily modelable things here, and this joint probability is somewhat difficult. That's one thing that I'm gonna use here. So I can do the easy math, multiply these two things, and I can understand that probability of AB is equal to probability of A given B times probability of B, right? So this makes sense because for A and B to happen at the same time, this antigen level and miscarriage, for this to happen, the miscarriage has to happen, and given that miscarriage, the probability of A. So I can actually model some things, the joint probability, using the two easy ones. Now what I'm gonna do is I'm gonna take this and I'm plugging it here. So I can then build something that's I'm trying to solve. So probability of B given A the thing that's difficult. And always I invite you all to think about the probability of B given A, not necessarily only healthcare related. So you can take this as the risk of not paying off the loan given some credit score, right? So the other way around is easy to model, but this B given A is the one that you're interested in, or the probability of having an accident for the driver's age or history and etc. The probability of anomaly given a picture. So this thing is the one that we're mostly interested in, and instead of the probability of AB here, what I'm gonna write is probability of A given B times probability of B, which the numerator is the joint probability as we derived here, divided by probability of A, right? So, and this makes sense because we assume that this A is happening and we need to normalize it by the prevalence of this thing. And probability of A can also, so this thing, let's talk about the probability of A. So probability of A is marginal over the joint. So we were able to find the joint distribution, at least write it in terms of things that we can model using our data science tools, and this thing is can also be described the same way. So this is a marginal, so we can talk about marginalizing over all possible B values, meaning healthy or unhealthy. So in this situation, there's no need to write the summation formula, but in order to present a more generic rule, I can actually write it as probability of AB, right? So I can actually write it like that. Or more easily, because the joint distribution is difficult, all possible B values, healthy, unhealthy, probability of A given B, probability of B. So what I have is that here this term, this expression here is referred to as the rule of total sum. I'm doing nothing but marginalizing. And there we go. So we have ourselves our formula, and let me summarize the base formula and talk about it a little bit and then conclude this video. So the thing that I'm interested in is probability of B given A. That's the interesting thing, and this I learned can be obtained from the thing that I can easily get, meaning probability of A given B. And I need to multiply it with probability of B, and in a second I will be talking about what each and every one of these means, and divide it by the probability of A, which is the marginal over each and every one of the joints, right? So marginal over marginalizing over all possible B values. So one thing that I would like you to notice here is that I would like to calculate the probability of B. That's the thing that I'm interested in. That's conditional something, my situation, but overall I would like to find the probability of B given A. And this probability is obtained from some probability of B that I think that's happening. So for any pregnancy, what is the probability of miscarriage independent of the observation? Do you all see that? This represents what is the probability of miscarriage independent of the biomarker that I measure, versus this represents what is the probability of miscarriage based on the measurement that I had last week, right? And also I invite you to read this formula the same way for the application, for the use case that you're working on. So we mentioned a probability, a prior probability, strictly speaking, of B, the thing that I would like to measure. And that's right, the name for this is actually the prior. So the base rule starts with the prior. And what's going on? I'm going to move to here, the second term in the base rule. I'm taking my prior and updating my information about the prior, the thing that I would like to measure, the B, based on my observation. So this thing is my observation. I'm conditioning it on. And with this, hopefully I'm having a better understanding of the thing that I would like to measure. And I'm now able to update my prior to posterior. So this thing is called the posterior. And at this point, let me stop and again talk about the prior and posterior. And always imagine, as data scientists, our job is to predict the probability of things that has not happened yet, or the probability of the things that are not easily observable based on the things that are easily observable. You can see this as this A is something that everybody observes or you can observe, but B is the thing that of interest. Think about it, this is tomorrow, right? So you would like to measure the probability of the stock price or stock market behavior tomorrow based on the thing that you're observing today, the news, the Twitter posts, the stock market behavior today, or not even only today. I can condition on several things, right? The stock market behavior of the past week, past year, and the Twitter news and the political news and everything else, right? So that's the thing that I would like to measure, the model. And this is based on a prior. And this should not startle you a lot because your prior can be uninformative. You may have no idea about what to expect for tomorrow, which means your probability of any outcome for tomorrow can be equally likely. That's also okay, and you can update this equally likely prior for the next phase. All right, here we go for the third term, and this third term is I'm observing the probability of the thing that I observe, and based on the thing that I would like to estimate, right? And this term, we mostly use the word in our daily lives in English too. What is the likelihood that we observe this? What are the odds? And the exact term of the thing that I observed, the probability of the thing that I observe, and our minds typically condition the observation on most of the all of the things that we cannot observe, and very quickly calculate the likelihood of our observation. And in machine learning, you might in basic machine learning approaches, you might have seen this term a lot, because mostly what we do is we try to find the best course of action that maximizes the likelihood of observing what we have observed, which is there's a very short term for this in data science. Observing what we have observed is the data, right? So the maximizing the likelihood of the data based on the thing that I don't know, mostly the model, right? So maximum likelihood based approaches does maximize this, but it's not directly, as you see here, pretty open, is not the thing that I'm mostly interested in. And last but not least, this is the term that we use to normalize our Bayes formula. So remember, A is the thing that I have observed, and using A, I want to make an informed decision about B. And A in pure math terms is our evidence. And this evidence is obviously not directly calculatable because I don't know if this evidence is coming from B or B not, or other possibilities of B. So therefore, the evidence calculation needs to be marginalized over all possible values of the B, the thing that I want to estimate. So that is Base rule for you.